Okay, so once again I'm going to talk about our project called Smart Juggling Balls with visual reinforcement, or visual amplification as I call it in this case. So I was supposed to deliver this part of the talk together with Trond Mikkelsen, who was there earlier, but unfortunately he had to go and take care of his children. So I'm going to do this by myself, and I'm sure Roger is going to help me out whenever I forget something I'm going to do. So basically what we'll talk about in this part of the talk is really the design process, because I'm an engineer and I tend to see things in an engineering manner, having an engineering process, engineering point of view. And then Trond, that I was working together, he's an artist, and he sees things from an aesthetical point of view, from a kind of, we have a little bit of different kind of views. So what we were going to talk about was really how do we talk together to be able to understand each other's point of view to make this work out. So that's a little bit of part of what I want to say. And I'm also going to talk about what's inside of the balls and how we actually design it, and some of the failures we did, because we had been going through this for a few iterations. Yeah, I don't have to think it worked out so well. So I'm going to say a few things about that. I think the way I'm going to do this is just basically to flash a lot of pictures, and then I'm going to talk about some of the constraints that we have and some of the desires that we have. So one constraint is that we have limited economical resources. So we can't just buy the most fancy things or produce things from the most kind of suitable materials. We have to do things in a kind of cheap manner. That was definitely a constraint we had. We had constraints in time. There's a limit to how much time we can actually put into this project, because I have a full-time job, Roger has a full-time job, and you have to be a little bit efficient, so to speak. So that was definitely a constraint. And then we had desires, because we want these things to look reasonably beautiful. And I think, do you use some of the balls that you just had there, or that you use for this part? But we try to, this is the very first ball we made, and it didn't work any longer, so I had to show the picture. But we definitely wanted there to be an even light. When we switch on the ball, we want it to be kind of evenly illuminated all over the surface. And in the very first iteration that we made, we couldn't achieve that. And it's not very visible from this picture, but in the first prototype we made, there was a lot of light on one part of the ball, and then there was light on the other part of the ball, and the rest of the ball is just kind of hidden in darkness. So that didn't work out very well. So one desire for this iteration was to have a much more evenly distributed light on the ball. Can you remember some of the other desires that you had in the design process before we started to do these things? Just remind me a little bit. Sorry?
Should be able to drop it?
Yes, that was an important part. Thank you. You have probably have to cue me a lot, because I don't have my notes my way.
Easy to assemble.
Sorry?
Easy to assemble.
Yes, sure. So it's everything. So obviously we want to have a ball that then we juggle, and if you happen to drop it to the ground, that's fine. I think this first prototype, oh, it even started to function. Can you believe it? It's magic, yeah? Wow, I should do this more often. But anyway, here you can see the problem with the light, that you know, there's like one little green spot there if it's illuminated, and then there's a little green spot where you use on the opening. Otherwise it doesn't work very well. That was the fourth thing. We wanted something that was easy to assemble. And this first balls that we made, I think you can find a picture. You can't really see it properly, but what we did, we took some of the juggling balls that Roger already had, and then we cut them open with a knife, and we tried it with some kind of plastic confetti, small tiny plastic parts that are used to distribute the lights. So we took them all out, put it in the circuit board, and then we had to re-glue it and kind of, refill all this confetti, and it was very labor intense. So to build a single ball, soldering all the parts and gluing it all together, it takes hours for a single ball. And if we want to make it 50 or 100, it's just going to take weeks. So we wanted something that was much easier to assemble. I'm not quite sure if we actually achieved that. Yeah, here's another picture of me trying to solder the very first prototype of the circuit board. And I was very lazy, so I couldn't be bothered to order RGB LEDs.
So we just took some LEDs that we had lying around, so we had like one single LED for each color, one red and one green and one blue. And of course it was a hassle to fit all this into the tiny tiny parts of the circuit board and make it kind of easy. So that also was very labor intensive, fitting all the LEDs and so on. Yeah, here I got some more pictures that shows the evenly distributed light. And then we tried to make the balls, the shell itself, of different materials. So we made one attempt to make an acrylic material that we milled out. And it's kind of good with an LED side, but it's very kind of hard and brittle. Yeah, it's acrylic plastic, very, very hard. So the idea was to put in a circuit board that fits perfectly, and then actually glue them together so that everything can fit inside. That was something we tried out. I think it worked out very well. Here's just another picture of the parts that are being sent around. These parts. We definitely wanted to have rechargeable batteries, so we didn't have to open them and change the batteries all the time. So we wanted some kind of different polymer or something. So we thought to charge it. So we tried out this design, which had a jack plug on the end, a 3mm jack plug. And the idea was to connect a little plug in here and charge the battery. And also use this as a switch because it's a kind of mechanical part inside. So whenever you unplug the switch, the ball will switch itself on and be used for juggling. That was an attempt we tried to do. It didn't really work out very well. A few more pictures, same thing, same design. This is pre-Arduino, by the way. It took a while before we had the brains, I would say, to do Arduino. And actually, I was the one who was very much against Arduino because I've been working a lot with microcontrollers for microchip, and I was very familiar with them. And I felt for a project that was quite labor intense. I don't have the time to learn and find new technology for this project. So I said, I just want to stay with whatever I have. And then Roger said, there's this thing called Arduino. Why don't you take it?
You were convinced.
I was not entirely convinced. And then he pushed me and he said, look at the code for the microchip. It's immensely complex. You configure analog to digital conversion, you configure all the timing and so on. A lot of really complex C code. And then he showed me, okay, Arduino, you just do analog read and you're done. And then eventually he managed to convince me. And that's also a bit difficult for me to actually listen to someone else who is not an engineer, not theoretical guys that teach me electronics. I'm not sure if I like that, but eventually I managed to bend me over, and I think that's a very, very good thing. So working with other people can be hard, kind of emotionally, but it's quite so this is pre-Arduino design. And before we went for Arduino design, we want to make sure that the radios that we had available could actually work with Arduino. So this is just a little hack that we did at the Roger's office at the university, where we put up radios and some Arduino stuff to see that it worked out well. And it did work out quite well. So then we did the Arduino design. So this is the drawing that I showed you in the previous talk with the eagle design that connects all the parts together and so on. Are you familiar with eagle? Do you know eagle? No, if you do electronics design, I would really recommend it. It's free, it works very well, and it has good library parts. And then of course, there's the PCB that has placed up all the components and so on. And I think I mentioned about it briefly in the previous talk. Here we had the Arduino chip itself. This is the HDI chip that takes care of the communication on the USB port, so that we can program it. That's why using USB. There's an accelerometer, which will be straight in the middle of the board. And then there are some fuses that make sure that if something is shorted out, it doesn't blow up and all that kind of stuff. It kind of protected electronics around it. Here's something that Trond made very briefly, because we wanted to see how the acrylic ball actually worked out the lights. So some blue LEDs on one side, some green on the other side, and we put it inside the acrylic ball just to look at the distribution of light. And we figured that even though it worked kind of okay, we felt that the ABS plastic material that comes out of the 3D printer distributes the light much better. So I think if you look at this very powerful green LED, that when it's inside the shell, it gives a kind of even and beautiful distribution of the light. Whereas the acrylic material is also like this. It tends to kind of be visible where the LED is located. It doesn't distribute the light as nicely. And that was also one of the reasons why the light was intended. Sorry?
I thought it was intended.
No, but it also makes a kind of bright spot when you look directly at it, whereas the plastic distributes light much more evenly. And that was definitely something desired. These LEDs are way too powerful though, because they draw like 350 milliamps, and the battery that we use is like 250 milliamp hours. So if you had two of these on each side, you drain battery in less than 20 minutes. And that wouldn't kind of good. So the blue side can go for different types of LEDs. Also in the process, quite early in the process, printed or cut out a small kind of paper copy of the PCB just to see how it fits all the parts and so on. That was also a useful part of the process. I should have a skip forward here. That's some pictures of the illumination test. At the early stage, you see 6 LEDs would be sufficient to give it a kind of evenly distributed light on the wall. Here's the content of the wall with the lid open. The same in blue. And we also did some tests on how much current do we need to push through the LEDs to make sure that it's sufficiently illuminated. So we spent some time in the soldering lab at the university, just playing with power supplies and so on the stage, just to see what it looks like. And then we started to solder things together, and we actually do this by hand. So we have a little straight, a little kind of injector thing and a little needle. It's filled with some kind of malleable solder stuff. And then manually we place this solder paste on each single pad, place all the components, and we bake it in an oven for like 2 minutes, and then all the solder paste melts, and the components are soldered to the circuit board.
So it's soft, and when it goes to the oven, it gets harder.
Yes, exactly. It gets into the oven. No, first it actually melts because the solder paste is just very finely granulated solder.
So
Then you heat it, and then it melts, and then you take it out, and then cools it down, and it can be solidified.
So inside the injection is not like one liquid, it's just small pieces of
Yes, exactly. And they are diluted in some kind of liquid that keep them kind of suspended with any squeeze sort of what is it. That works out pretty well, even though some of the smallest chips, especially the paste on the FDI chip, occasionally they get shortened. So we also always have to do a little bit of manual labor on each single board before they are working perfectly. And here's a fully assembled board. So you can see the big radio on the backside, which takes care of the communication. It is the accelerometer in the middle somewhere, and then this is the Arduino chip itself. And these small green parts here, the EV brake loaded, on this side and on the other end, but you can see properly because of the light. These are actually the fuses that goes to the battery, so that if something on the circuit board shortens, the fuse will break the connection for a little while to make sure that we can fix the problem, and then the fuse will reconnect when it cools down again.
It's like a temperature fuse.
Exactly, it's a thermal fuse, so it has a positive temperature coefficient. So when it gets warm, its resistance increases.
Is this not in a big component, or is it on in a certain amount?
No, they exist in all kinds of cycles. So here, the current is limited to 350 milliamperes, which is suitable both for charging the batteries and for running all LEDs at full strength. But you can get them at any kind of current level, and also physical kind of size. Obviously, if you want tens of amps, then they're going to be quite physical. They dissipate easily. But anyone who has tried to shorten a lithium polymer battery knows that these fuses are very useful because they can deliver an awful lot of current and it's very hot. So it's very useful to have a fuse. And here's 5 of them connected together, and Roger wrote a little test program for each of the circuit boards has a unique ID, and then one of them broadcast, and then the next one is illuminated, and then sent and so on. So just that we can test that the radio is working, that the LEDs are working, and so on. It's a little sample program to make it work, see that things work properly. And then comes the challenge of the weight, and this is really a story which I think is interesting, because the plastic shell of the ABS printer is very light, and for the balls to be good to juggle, we need to add some mass to them. And we had different ways of doing this. I took silicone from that was used for bathrooms to seal things between pipes, and I then injected into the balls so they were all filled up, then it became way too heavy. And also the silicone smells bad, and it takes months before it dries out. So, and I was so happy I filled up my first one with quite heavy, and I came to Roger, and he was just like, "What have you done? This smells disgusting, I don't even touch it." So then we went for a different attempt, and yeah, so we use something called candle gel or candle wax, which is used to make kind of small candles. So it's a kind of paraffin or something, a kind of chemical that burns very easily. You can heat it a little bit and it melts, and it becomes very malleable. So Roger made these kits, and we actually took this and put a light bulb inside each little half of the ball, and then he would melt all the candle gel and he would pour it into the space between the light bulb and the shell. So here's a great picture of hardcore juggling science in the kitchen of Roger's apartment. Yeah, there were several of them. And I think it actually gets pretty messy, so you need to put the newspapers on the floor and all over the place. The good thing is that when he was done, he had a perfect weight. There were 70 grams for the total combined. And when we put in the electronics, I think the weight increases to 93 grams, which is exactly where you want it to be. So he managed to get to place the light bulb just at the right height to the material. And of course, when you plug in the circuit board, the material, the candle gel comes out, so you have to clean it up. So yeah, and then we're doing the serial production in its kitchen. Here's a picture with the electronics fitted inside. Here's another one. It gets quite messy, but it tends to work quite well, and the stuff sticks to the surface of the ball quite well. That's cool. But of course, the printing process of these kind of the balls are made at the National Academy of the Arts. Trond is working. So here's just a picture from the printing process. So it's a 3D extrusion printer that prints it layer by layer. It's very thin layer by the top was plastic in different layers. This is just some pictures from the printing process. So we have just started to print a small part here, and this is the opening for the USB plug that comes out in the end of the ball. Very, very tiny part. And here is a picture of the final product. Yeah, I think that's what I had actually. Do you guys have any questions about this, or anything else you would like to hear more about? Yes, sure. So you want to go first? You want to go first?
I have a very commercial question.
Sure.
I assume it might have been a couple of thousand hours that you spent.
I think it's how much 1,000 hours.
So if you count the three of them together?
Yeah, do you have any number? No, I'm not quite sure. Maybe the three of us combined, I think. Yeah.
In terms of financial funds?
Yeah. We did this initially as a project to do public engagement. So we want to use math and juggling, which that we talked about years ago, to encourage kids to be more interested in math and programming. So when we go on a festival or play with children and go juggling, kids basically don't ask, oh, what is this, what is going on? And then kind of have opened the door, talk about electronics, we talk about computation and so on. So that was kind of the initial idea of the whole project, that's where it started. So we wrote an application to do some research questions, have a program called Dyre, profiling the natural science topics. And they say we really believe that this project is good. So they funded us with 180,000 Norwegian kroner, which covered material expenses. It's 18,000 euros. 20,000 euros. So that covered all the material expenses and also a little bit of rates that we get into the paper. But now that I'm working in a different company, my company is very happy for me to do things that involves public engagement and giving talks like this. And that's why I can go and do these things as a work with that we pay for my employers.
Just came to mind material, but there is plastic little balls. When you boil it, it becomes flexible, so it's a bit hard. But you can make a shape of it when it gets cold.
It's solidifies again.
Yeah, but it doesn't break and it's not so hard. So probably this in a shape could be like the ball. And that's
yes, I think that's the thing to work on to make a mold that is stamped out. Yeah, that's something we're trying to integrate into this because. The ABS is good for certain things. It distributes light very nicely and very usefully. But when you drop it to the concrete floors from 2 meters, they tend to break apart and they can stay together, so that doesn't work out that way.
Which temperature range do you have? If it's melting at 30 degrees or in the summer, it is melting or is it?
No, I'm not sure the camera jet. I imagine it melts maybe at 70 degrees. 80 degrees. No, I don't think there's a risk of melting at that.
what kind of idea that you say about aluminum?
Yes, so I spoke to another guy, who's a mechanical designer, and he suggested making the shell of the boat aluminium, like 3mm aluminium casing, and then drill a lot of small, really fine holes in it, like hundreds or maybe thousands. Because he had seen some electronic parts made that way, and the LED behind, he said it looks like something that comes out of Trond, science fiction film. So if we can find a way to try
it's like a speaker of an aluminium case of the...
Yeah, exactly, on the back, exactly. So that's something we hopefully can find in the future, but I would imagine that milling aluminium into that right shape and drilling all the holes is quite a time-consuming process and it requires a bit of infrastructure. So I'm not sure if I can find anyone to actually pay for it. Because I'm not going to stand there and handle this myself.
The 3D printer you have in your work or?
No, the Trond was there, he works at the Norwegian Academy of Arts.
Yeah, that
And they had a laboratory called D-Form, so the laboratory for digital form, and they have different types of 3D printers, they have laser cutters, CNC machines, all kinds of stuff, water high power cutter. So he's the one who did all the mechanical part of the project.
What question do you think it costs to buy one now?
So how much does it cost to buy them? Yeah, I think that the balls that we have made now, because we were limited in time, we didn't think about using the cheapest component or the smallest component and so on. So just the raving alone, for one ball, costs like 300 Norwegian kroner, so like 35 euros. And obviously you want to set up the three balls that can cost you hundreds of euros in all parts. But we are looking into cheaper kind of technology in the context of trying to commercialize the project. And we hope to get the cost of a single ball down to say 10 or 12 euros at least. But that's a bit further ahead, so there's nothing commercial available at the market at the moment.
Probably the commercial way is get a cheap programming for this function.
Yeah, there are different ways to do it. You could imagine that you just buy a ball that understands sidestep, that the math of the juggling patterns, or you could imagine that you buy something in a simple interface that people can program it to be, or each time you scroll it to change its color, for instance.
You can even teach you the ball pattern later.
Yes, you have lots of different ideas. You have like for guitar, you have Guitar Hero. What about Juggling Hero? You know, so three things together. You have to go for one, and if you do it correctly, you get points, and otherwise you don't get points. So you can imagine these kind of things that the ball changes color, you have to throw in a certain manner, for instance. And you have been thinking a lot about an art works for different social games. So you can imagine that each one of you in the room gets a ball, and when your ball changes color, you have to do something with it to make it change back to the normal color. And if two of you change it at the same time, then you have to do something together to make. And then you can imagine all kinds of social games.
And then you go to baseball.
Yeah, exactly. Smash the baseball. That's how it definitely works out. You can imagine that this technology, because it's distributed, it doesn't rely on a centralized computer. It can be used for all kinds of distributed simulations and experiments. So it's really about, I think that we have enough ideas to what we really like is time and spending to sit in studio, because it's very time to make builds from scratch.
If you think about the musical way of using this technology, like I would instantly think of drumsticks.
Yes,
the same technology, because you have the same problems of combinations of patterns and rhythms.
Yeah, that's right. So earlier today, Roger gave a demonstration where he was juggling, and based on the type of throw, high throw or low throw, all the kind of same hand, the balls would produce a different sound.
Yeah, exactly. That's what brought me to the idea that you could easily use that in an educational musical way. The idea. Did you think about that?
No, not in the context of musical education. And I think that's because I have no experience with neither music or education, so I don't think I'm really right person to kind of think about these issues. And I think we are not exactly experienced musicians either, so. But oh, sorry. So we have thought a little bit about using musical instruments, but not in the context of education.
And my second question would be, in your research, which percentage is education and which percentage is just fun? Because you obviously seem to have a lot of fun developing things and presenting and enjoying it. Is it how much is it a fun project and how much is it a real educational approach that you want to push forward?
I think on Thursday when we're going to talk to the research council, we're going to say that, oh, this is a bit fun, but you really because you want to encourage kids to do natural science. But with you guys, I can say that it's probably 50-50. I really do believe that encouraging kids to do natural science is very important. And Norway is a situation where there's a huge lack of engineers, so we really need to encourage kids to go into that kind of direction. So that is an important part for me. But also I think actually building things and seeing it work is also such great fun, so that's at least for me an important part.
That was my assumption, 50-50.
Yeah. And then maybe I'm a little bit too polite towards the education part.
Okay.
I'm working in a school, and could we just maybe arrange that you come and we can show this, or that we arrange something? It would be really nice.
Yes, I think that would be really great fun. And there are several schools in my kind of local area that are Martin and Roger to come and give talks. And I think we are trying to do a few of these in fall. But we also try to do, in November, we had an appointment to give a talk for all the teachers in the city where I come from. So we take all the teachers from all the different schools and invite them to the local cinema, and we give them a one-hour talk about math and juggling, so that they can be a little bit enthusiastic when they talk about natural science and computing. So hopefully that when the kids come and ask for help what kind of education they should do, the teachers can talk about natural science with a little bit of genuine enthusiasm, instead of making them do really serious studies. So if you can arrange something to come and give a talk over that, is that good? Yeah, we would love to do that. Sorry? Norwegian too, yeah.
Also. And I had the idea about the question about how did this idea grow? As a you juggle, and then you said, okay, there's technique, we are technicians, we are engineers, so then it grew like this, or?
It's funny that you ask, because I did my PhD in Bristol Robotics Laboratory, working on small tiny robots. And then Roger came to visit the lab and he gave a talk about juggling, and wow, that was really cool. And then Roger said, is it possible to do measurements on these kind of things, to do things? And I said, well, I have these robots lying around and they have accelerators and so on. So Roger taught me to juggle kind of very basically, very kind of simple, and I said, well, I need to find this out, so I had to juggle the things in the center, because it's very expensive research robots. So when nobody was looking, I was kind of looking and go juggling, and I dropped it a lot in the beginning, but it did great, but it's very like robots for 700 euros each. But what we do for science, then you have to make some sacrifices.
So it grew, and then it...
Yes, so then we discovered for the measurements that it's easy to do free fall detection and catch detection and ball and throw detection and so on. So I sent lots of measurements to Roger in Oslo. I was in England at the time. And then we spoke, and then he said, let's see if we can do a simple prototype. So Roger spoke to some people at the university. I then had a meeting with them, and they gave us a small amount of money to build the very first prototype. And that kind of worked out well. We liked the idea, and then we applied to the research council that funded this part. I think I've seen it there. So it was we made a personal effort to make it any action on people to listen to others.
But it started off just with a cool idea. Wouldn't it be cool if we had these balls with these, accelerometers, and perhaps they can communicate with each other? And it starts off just like a what if idea. And then, what if?
Yeah.
We should make this with Diablo as well. And then there's people play Diablo, juggling, and then people make music out of this, and there's like a show. There's a lot of potential, I think.
What I think is interesting about contemporary manufacturing is that I can sit at my computer, I can do a design of PCB, and then I can send the file to somewhere, and then after a few weeks it comes back in the mail, and it isn't too expensive, even though I just only make 10. I don't have to make a million to drive the price down. So therefore, I think the cycle can be quite short. It doesn't cost too much to actually have things, made of the proper PCBs and so on. So, when we say Diablo, then you just go home and design a Diablo board that fits with the kind of Diablo thing, and then you can have it running in a month. It's impossible. So ideas I think are easily available, ideas are almost cheap. What is the expensive part is actually the time that happens to make a very new program. It's quite time consuming to do more and more.
And another question is patent or so? You have patent on this, or it's just like you're playing and make this and
so we sent this idea to an idea competition a year and a half ago, I think, and we came second. And the second prize was to have 10 hours free with a patent lawyer from a patent office at university called Dental. And they liked the idea, and we have now 5 temporarily claimed the idea. And we are making an evaluation this summer whether we should actually go further with a commercial product. So to make a proper patent is quite expensive, because quite a few thousand euros. And we only do so if we believe that the market potential can bring this back to us somehow. So this kind of trade-off. So we are talking to manufacturers that will help us to produce things cheaper and easier. And then we have to make a decision whether we think it's worthwhile to continue with this kind of commercial
But sometimes it's very different part from what you like to do and what you're doing.
Yeah, because I think it's tempting, I can make moves and everything's in a way tempting. But I think that the market for intelligent juggling balls aren't really going to be that huge, It's not like everybody will have a set of intelligent juggling balls. So.
But then you need to collaborate with some companies to do it, because your time is not doing the thing, then your time is doing the management.
Yes, exactly. So you need some kind of business partner to make it work like that. No doubt.
Well, that the Southeast Asian company that builds the juggling balls after all we pay the license fee.
There's always a risk of being screwed over, particularly if you are small and
it's something that's I guess again would be a rather cheap, low-priced item.
I think so too, yeah. You have made it cheap to pay possible.
Can you reprogram it over USB?
Yes, that's the whole point. So you write code on Arduino, and you just plug it into USB and you push upload, and then it uploads and you program.
Not over the radio.
Not over the radio, no. And that's because the radio is quite has got little delays. So whenever you send the bytes over to the Arduino, the CPU acknowledges that, okay, I got this string already into the flash memory, or set in the next part. And I think the delay is just too much, so it becomes not very fast.
I was wondering if, for example, if you take new toothbrushes, you have contact with e-charging buttons.
That's right, yeah.
And if you put over-the-air updates of the software, then you can really close the mouse.
Yes, that's true.
So
that's true. So what we have done with these balls is that we have actually several programs running in the ball. And then we just send a single byte over the radio. Use this program, or use that program, or whatever. So and that control program is written in processing. So this is all in Norwegian, but the leftmost button says everything off, and then I have the next one which is everything on. And then it just switches on and off the colors. And then I can put it into 0G detection. So it is it is pink and it's blue. Oh, it's not blue there. It should go blue here. Oh yeah, there it is. So in a way, it's not programming the ball, but it has to change which program is behavior and stuff. Which is programmable. Yeah. And the Arduino microcontroller that we use has 2 kilobytes of program space. And I think for this program, we're using 7, I think. So you can actually put a lot more in there if you want to. It's a little space available. You can do much more complex things than I think it's going to upload.
Can you program to make the light frequency like flash?
Yeah, sure. You can do that. As a matter of fact, it is flashing this very moment at 4,000. No, it can't do it because it's 4 or 5,000 hertz. 4 kilohertz.
It's very nice when you play with the eye.
Yeah, I think you find it quite annoying when the juggler actually are flashing in the right frequency. It probably doesn't big fit, So because as Roger mentioned that they had a peak detection, so that it flashes on the very top, and that for a few milliseconds, and it's really annoying. But the juggle and it seems like both faces for a short time, you kind of lose track of how it's actually moving. So you can do things that are really uncomfortable if you want to. Yeah. Okay. Any more questions, or are we?
I had about what you use to program this.
Yeah. So Arduino comes with its own kind of programming language, which is very similar to C. But it has a few built-in features, so automatically there's a piece of software called loop, and whatever is written in that loop section, it just repeats itself continuously. So it's a kind of simplified C. However, what we did for this project, because there's a lot of hardware involved, we wrote a C++ abstraction layer class, a hardware abstraction layer, that takes care of sampling of the sensors, doing the 0G detection, and so on. So it's just kind of hidden away in an abstraction. And then when you start the Arduino program, you can make an object on the wall, then you can add the ball in the air, and you can make this, this program is just like 6 lines of code, and there you are, so it makes it very, very simple. That's the complexity in a way, in abstraction. Okay, I think that's it. So I thank you for your attention.
Thank you.